Hello? Okay. Okay, so this is one where you could do it either way. All right, so you can do a quotient rule, or if you see it, you can do it this way. This really only works well when this is very, very simple. If it's not very simple, then doing that breaking apart process gets pretty complicated. So again, this is a case where your first question is always, is it a basic? Or can I easily make it a basic? If not, then you're stuck with product or quotient. Yes?
But, I mean, in theory, it's always possible to do it that way, right?
Yes.
It would just get so complex.
Yes, you'd have to actually do polynomial division.
Right.
Yeah. Yes.
You did 2 different answers.
Oh, I didn't. This I'm just rewriting y. So then when I find y prime, remember the rewrite is not the derivative. That's a mistake some people made on the test as well. The rewrite is just rewriting the function a different way. The derivative here would be 0 plus 7 times negative 3 to the x minus 4, negative 21 to the times x to the minus 4. Yeah.
And for the denominator, aren't we supposed to keep it in b squared?
In this case, if it cancels, cancel. That's how you simplify.
Okay, so we only keep
Oh,
it.
b squared when it's something you'd have to FOIL out. Yes.
Okay.
Thank you for clarifying that. Right. So if it's x squared plus 3 quantity squared, don't FOIL that out. But this is the case, yes. When it's simple, you want to try and simplify as much as possible. Yeah. Okay, so let's look at another couple. And you will be happy to know that the applications are not new. The applications to this are all the same ones we have already done. So when we get here shortly, we'll do some applications, but they should look really familiar, just a little more complicated derivative. All right, so let's look at this one. Find y prime for y equals x minus 2 over ln 2, ln x. Ln 2, what do I think about ln 2 while we're talking about lns?
Number.
Ln 2 is a number, so as it's written this way, is this a basic? Yeah, ln 2 is a number. So it's just just divided by a number. But that's not what I meant to write. I meant to write that. So yeah. So ln 2 is a number. E squared is a number. So just remember that if there's no variable in it, it's a number. Treat it like a number. Tag it along the way where it goes. All right, so this one now, is this a basic? No, because I clearly have one function divided by another function, and there's no way to clean that up, no way to simplify that. So let's go ahead and look at the quotient rule. Bottom times, I'm saying it, but not writing it. Bottom times derivative of the top, which is 1. Minus the top times the derivative of the bottom, which is 1 over x. All over the bottom squared. And I'm going to write it this way. Do not just put a square. Without the parenthesis, the square will apply to the x and not the ln. You're taking that whole thing and squaring it, not just the x, but the ln of the x. So make sure you get the square in the right place. Okay, so let's clean this up. Ln x minus x minus 2 over x all over ln x squared. Can we leave it with a fraction inside of a fraction? You're saying, yes, please. And I'm saying, no, you can't. Okay, so what is the easy way? It's a phrase called clearing fractions. What's an easy way to get rid of this fraction?
Negative exponent?
Yes, but that doesn't help you because you need to write it with no negative exponents either. I could try and get this all over one fraction. That's a mess. There's actually a really easy way. Is there anything you could multiply this by?
X.
Yeah, so if I multiply the top by x, then this goes away, and that just gets an x ln x. If I multiply, can I multiply the top by x just because I feel like it? No, that changes the problem, but could I do this? Yeah, now what is this? This is equal to 1. I haven't changed anything. So I'm picking a creative value of 1 that's going to clear the fractions. That's the phrase we use. And so we pick whatever we need to clear whatever we need to multiply by. So if this were divided by 3x plus 1, I would have to multiply it by x and 3x plus 1. Whatever I need to clear all the fractions. So let's do that. Remember that this multiplies everything in the numerator. So x times the first term, x ln x, x times the second term. I should not get a fraction, that was the whole point, was to clear the fraction. So x times this, I know this x will cancel with this x. I'm going to keep my parentheses until we are ready, because it's not minus x minus 2, it's going to be minus x plus 2. What goes in the denominator? X, then x squared. Okay, and then you can just, we'll just clear up the parentheses. So be careful with your parentheses. People are not using those, and that means you end up, particularly when you have a minus sign in front, you end up, or multiplied by a constant, you're ending up dropping pieces. So please keep your parentheses until you've used them. Okay. All right, so one last one, and then we'll look at some applications. All right, find d dt 1 over t squared. So our first question is always, is it a basis? I'm seeing some nod yes. Are there really two ways we can do this? There are. We'll do them both ways. Does everyone see how this is a basic? Because I can rewrite this. If you can rewrite it into something that you know how to do as a basic, then that counts as being a basic. So I could rewrite this way. Right, and then we know how to do that. Or if you put it in a denominator. So that's what we expect to get. So let's do it using the quotient rule, just in case you didn't see that. The quotient rule still works, we just need to be careful about derivatives. So here, we'll start with the bottom. What is the derivative of the top?
0.
0. That's why it's going to simplify really quickly. Minus the top, 1, times the derivative of the bottom, 2t. All over, can I go straight to t to the 4th, the bottom squared? All right, so this term, 0 times anything, that one goes out. So now I have minus 2t over t to the 4th. Yes, you cancel to simplify. Minus 2 over t cubed. So the same answer. So again, either way works. This is definitely the easier way if you see it, but if you don't see it and you do this correctly, you will get the same right answer. So again, multiple right ways to the same one right answer. Okay, so let's just come back here and review kind of this list over here. Let me clean this up a little.
Wait, question.
Yes.
Wouldn't it be on the bottom 4t to the third?
No, because it's the bottom squared, not any derivatives. Remember our quotient rule. Bottom times derivative of the top minus top times derivative of the bottom, all over bottom squared. There is no derivative down there.
Got it.
So it's t squared squared. Yeah. And that's something, so that's something that people did on the test when faced with something like t squared plus 3t. We now know what kind of a rule do we have to use here. Is this a basic? No, it's a function times a function, which means the answer is most definitely the derivative is not equal to the derivative of the first times the derivative of the second. Is that in our product rule? No, the product rule has two terms. If you write down one thing like this, you know you have done it wrong, because the product rule will have two terms. Each term has one function and the derivative of the other function. And then it flips for the second term. So this is not correct. Now, you could multiply this out. On the test, that's what you were meant to do, is just multiply it out, and then it's an easy one to do. But you can't just take derivatives of pieces. Yeah. Okay, so any questions so far? All right, let's look at some applications. So tell me some applications of derivatives. When do we use derivatives? Marginal analysis, that's a good one. Slope, yeah, slope of what?
Continuous Tangent lines.
Tangent lines.
Oh, I got one.
Okay, good, go.
When we want to ruin the economy.
Yes, derivatives, those kind of derivatives are slightly different than these kind of derivatives. Yes.
Single comma.
All right, so tangent lines, finding the slope, finding the equation, finding where the slope is equal to 0, right? Those are all, these are, guess what? These are the ones you've already done, and these are the same ones we're doing. So we're not adding anything new. Depreciation is actually a form of marginal analysis.
Right.
Right. So we're not adding anything new in terms of applications. All we're adding is now we can do it with more complicated functions. So let's look at this example. We've already done this derivative. So you'll have to remind me what it was. I didn't write it down. So we're going to start with this one. Find the equation of the tangent line at x equals 1 for f of x equals 2x squared over x squared plus 3. So, reading this problem, I'm going to use lots of abbreviations. How do I know what I need to do? Find the equation of a line. So the first thing I know I need is a point and the slope. I have to have those two pieces. So, what kind of, yes, so I have an x value. I already have this piece, 1. I just need the y value. Where do I go to find the y value?
Plug in.
F of x. So remember, y equals f of x. The slope is equal to the derivative. So if I want to get the y value, I just plug into f of x. So if I plug in 1, I'll get 2 over 4 half. So this came from 2 times 1 over 1 plus 3. Where does the slope come from? It's not any old line. It's a very specific line. What line is it? It's the tangent line. So because it's the tangent line, that means we know that the slope comes from the derivative. So the derivative, once we find that, the derivative is a formula for the slope at any point on that graph. So the first thing we need to do then is to find the derivative. So let's come over here. And we already did this, right? Can somebody go back in your notes? This was, well, I called it example 5, but I didn't number it, so let me write it down. Anybody remember what this was? Negative, no.
I don't know, you can split it up.
Well, I can, but this is a complicated denominator, so I'm not sure I want to split it up that way. This is the one where you have to get a little creative in your splitting. You have to add, subtract some stuff at the top.
12x over x squared plus 3x, all that squared.
Yeah, there we go. So we've already done this one. So I'm not skipping steps. We did this one earlier in class. And we did it using, is this a basic?
Are you pointing to just the top?
No, with 2 fingers. Is this a basic?
No.
No, it's not a basic, right? Because I have 2 pieces, the numerator and denominator, and the denominator is not easy enough for me to mess with it. So this is a quotient rule, and we already did that. All right, so now what do I know? I have my point. I get my slope from plugging in there. So I want f prime of 1. So 12 over 4 squared, 12 over 16 3/4. Did I do that right? I think so. So now how do we put these together? I prefer the y minus y1, this one. That's my preference. If you guys like the y equals mx plus b method, feel free to use that. Totally fine either way. Just remember, when you get to the end, if you use y equals mx plus b and you get b equals something, you're not done yet. Now you need to go plug that back in and write the whole equation. I like this one because once I plug in and solve for y, I'm done. So we'll have y minus a half equals 3/4 x minus 1. Yes, did I do something wrong?
12.
Where did I get 12?
Yeah, where'd you get 12?
In what, in here or over here?
In general. It's not.
We did this work before. This is a previous example. So we did this derivative already. I pulled this out of our notes from previous. Right. Yeah, so no, because you can't pull this. Do not do your homework and write down this one line. because I will know that you copied from the back of the book and did not do the work, because I can't do this in my head, and if I can't, I'm going to assume that you can. There are a lot of steps that go in here, right? So I didn't pull this out of my head. This is just work we did before. Yeah. Okay, so y equals 3/4 x minus 3/4 plus a half. Does that seem right? Minus a quarter? Yes, the answers are in the back of the book for the odds. Yes. Okay, so find the equation of a tangent line. Find the equation of a line, point and a slope. You get your y value from the function, your slope value, because this is a very special line, it's a tangent line, the slope comes from the derivative. So you have to have done the derivative first. This is a quotient rule setup that we already completed earlier in class. And you just plug in and work from there. Okay, so what about this one? Where is the tangent line? What's the next word I'm going to write? Where is the tangent line?
At.
Well, horizontal. Let's just ask that. Where is it horizontal? For f of x equals 3x cubed e to the x.
Yeah, that is the same as that.
Yeah, we've done this one already, but let's just, I'm going to do this. I'm going to change that. Sorry. Let's just make it a new one for practice. 3x squared plus, I'm making it up, I know, it's really dangerous. It's always really dangerous when I make it up. Okay. All right, so where is the tangent line horizontal for this function? Let's break down the sentence. Where? What is the answer to a where question? X. Where is always an x equal? So I am looking to solve for x. Tangent line horizontal. What is 0?
Slope.
The slope of the tangent line. How do I get the slope of the tangent line? The derivative. So this is saying slope equals 0. That's what horizontal means. Tangent line is saying that the slope is the derivative. So that means all in all, I'm going to take the derivative, set it equal to 0, and solve for x. So I need to find the derivative. Is this a basic? No. It is a first. Is it a quotient or a product? Product. Okay, so you guys do it, and I'll do it, and then we'll regroup. Oh.
That's what you get for making it up, right?
That's what I get for making it up. All right, hang on a minute. Hang on a minute. Ah.
What's the problem?
I haven't gotten that far anyway.
All right, we're gonna go back. We're gonna go back to so. all right.
Didn't it just become the same?
No, it became much harder. All right, let me try this again. All right.
I know, because I got it. I was like, whoa, wait a minute.
All right, let's try this one. Yeah, let's try again. So is this a basic in general? No. It is a product. So go ahead and do the product rule. Yeah. Oh, I just almost made it really, really hard. Yeah, I did, yeah. Sorry. So say it in your head. First times derivative of the second, plus second times derivative of the first. Try not to slur your derivatives like I did. I'm assuming everyone got the first step pretty well, first times, these are easy derivatives. It is important for exponentials, particularly if you're going to set this thing equal to 0, you need to remember what we talked about before. The exponential goes second, all the polynomial pieces go in the front. So because there's an e to the x common, I'm going to pull that out, that leaves 5x squared here and 10x there. So what do we know about two things multiplied together equal 0?
That one was 0.
What, exactly, one of them is 0. So either this one is 0, or that one is 0. That's how we do it when we have polynomial factors. It's not any different. It's not any different. Two things multiplied together equal 0. One or the other must be 0. Okay, let's start with this one. Is e to the x ever 0? When x is 0, e to the 0 is 1. Let's think about what the graph looks like. This is where if you know your graphs.
There's an asymptote. So
Asymptote. Does it ever get to 0? No. So this one gives you no answer at all. No problem. That's okay.
It's at infinity, right?
Never actually really gets there because, yeah, it's headed there, but it's never getting there. That's a limit versus an actual value. The limit is 0. The actual value doesn't exist. All right, so put this one. Can we solve this one? Yeah. How do we do this one? Factor. All right, so 5x, x plus 2, x equals 0, minus 2. Okay, so this is the same. Where is the tangent line horizontal? Horizontal is 0 slope. Tangent line is derivative slope. So where is the derivative equal to 0? Where is an x answer? Okay,
Pardon.
okay, so let's look at one last one. Rate of change. This is models, marginal analysis, estimated, all of that. Okay, so here's one. This came out of the book, but I didn't write down which one. Okay. So a communications analysis company has installed a new satellite television system in a city. The total number in thousands, so remember when we talk about the number n in thousands, when you see that? When you see that phrasing, that means 10,000 means that n is equal to 10. So it's saying that the 1,000 is already, we already assume that. Okay, so we don't plug in 10,000, we would plug in 10 for 10,000. So the number n in thousands of subscribers T months after installation is given this way. So here's the number of people based on the amount of time, months, is this. Think about this. You would expect, I believe this graph looks, I'm going to say it looks like this. I'm not certain. But let's think about the limit. As t gets really large, let's do this one as a review. As t gets really large, like infinitely large, like if this were in place forever, what would I expect for the number of subscribers? When I'm looking at infinity, only when I'm looking at infinity, that's when I can disregard other smaller pieces, right? Because infinity compared to 4, the 4 doesn't count. So this is where I look at leading terms. 180t over t, 180. So the limit is 180, 180,000. That makes some sense, right? You go into a market, and first you have kind of some gradual increase, and then it gets, people start hearing about you and you get more, and eventually you've gotten as many people as you're going to get, and so it tapers off again. So this model makes sense. Okay, so let's look at the question, which is find, the first one is find n prime. So part A says find n prime. Is this a basic? No. Can I make it into a basic? Not easily. If this were flipped and the 180t was in the denominator, then that would be simple enough, but no. So what rule must I use? Quotient rule. All right, so let's go. Bottom times derivative of the top minus top times derivative of the bottom all over the bottom square. So I would encourage you not to copy down what I'm writing. I would encourage you to do it in parallel with me and then look up and make sure you got it right. That's a better way to practice in class than to just copy what I write. Okay, clean up. Yep. So this will give us 180T minus 180T, so those are going to cancel. So 4 times 180, 720 over T plus 4, 180 squared. All right, so the next thing is to find n of 16 and n prime of 16 and interpret. Remember what interpret means. Finding these numbers is identifying. That's just putting the number in. Interpret says, what do those numbers mean? What does it mean to have a value? So n of 16, you divide by 20, right? Am I right? That'd be 20. So 9 times 16, you do it on a calculator, I'll do it in my head. 9 times 16, 10 times 16, 60 minus 16, 144. I'm getting 144,000. And here, 20 squared would be 400. 72 divided by 40 would be 9 divided by 5, because they're both divisible by 8, 9 divided by 5. So I'm getting, do it on a calculator. Somebody check me. It's fun to do it this way, but no, check me. Anybody get these numbers? Both? Okay. So what do these numbers mean? They don't even have units on them, right? A word problem has word answers. So what n is what? Is it dollars?
Numbers and thousands.
Numbers and thousands. In fact, this is what I got.
Right. 18.
Yeah. 18 and 1.8, 1.8 or 18? 1.8? Yeah, so this is actually what we computed, so I was getting ahead of myself. Are these dollars? No. These are numbers and thousands. So this tells you that at 16 months, the current subscriber number, current subscribers are 144,000. And what does n prime tell us? I know that's 1,800, but 1,800 rate of increase, right? Because it's positive, I can say there are 144,000 subscribers increasing, each month increasing at 1,800 subscribers per month.
At 16.
Right, at 16 months.
Right.
Right, so at 16 months, I currently have 144,000 customers, and I'm increasing, because this is positive, I'm increasing at 1,800 customers per month. So the interpretation, and I took off a half a point on the test for people just saying rate of change is 1,800. You can do better than that. Because this is positive, you can say that it's increasing at. You can put another layer of interpretation on that. Okay, so then the last part of this question is, use marginal analysis to estimate the number of consumers at 17 months. So use marginal analysis. That means use the current trend, the derivative. So this is saying I just want to go 1 month later. So at 16 months, I'm sitting here at 144, and I'm increasing at 1,800. So at 17 months, where do you expect to be? How would you figure that out? Yeah. Remember, 16 is your starting point. When you're doing marginal analysis or estimation, 16 is the starting point to estimate for 17, to project for 17, to approximate for 17. So you always start here. So we're going to start with 144,000. That's our starting point. And we're going to add. I'm looking for the total number. I'm not asking about what is the rate of increase. I'm saying estimate the total number where I started plus what my trend is telling me. Does that make sense? So it's a little bit different than saying I'm not asking about the rate of change. I'm not approximating that. I'm approximating the actual total number. And so that's it. Start with my total number, follow my trend. Could I go out 2 months? I could probably use this to estimate maybe for 2 months. Could I use it to estimate for like 10 months later? Probably not, because